Well, let's say we had this function. So, okay, we're in Co-17C? Yeah, Co-17C. Today is January 10th, the year 2024. Let's say we had this function, f of x comma y equal to 12 minus 8x minus 6y. We're gonna do a few things with this. But first and foremost, I just want you to be aware of, you might need to evaluate a function like this at a pair of points. It's the same as evaluating a regular function of one variable. You're just plugging in two things. So for example, if I said, what's f of 3 comma negative 2, we're just plugging in 3 for x and negative 2 for y. And that's going to equal 12 minus 8 times 3 minus 6 times negative 2. Whatever that turns out to be. 12. Let's see. I think I happened to pick something where it's going to turn out to be 0. That was not by design. I just made up numbers. Minus 24 plus 12. And yes, 12 minus 24 is negative 12. And negative 12 plus 12 does happen to equal 0. Or we could plug in two other points. F of 1 comma 1 would be, I don't know, you guys figure it out. Figure out what f of 1 comma 1 would be. I'll give you a few seconds to do that. Let me look at the pens here real quick. You're good. You're good. You're trash. You're trash. All right. So let's see. We should get 12 minus 8 minus 6, which is 12 minus 14, which is negative 2. Or 4 minus 6, which is negative, whichever way you want to do it. Be careful here though, right? It's not 8 minus 6, it is negative 8 minus 6, which is negative 14, and then 12 minus 14 is negative 2. Some other things about this function of two variables. I'm trying to think about which direction you kind of want to do this in. Let's talk about domain for a second. So when I think about the domain of this, or when I am asked about domain of any kind of function, I'm looking for three things. Is there a fraction where I might divide by 0? No. Is there a square root? Is there a logarithm? If I don't see any of those three things, odds are there's no domain restrictions. Now, I want to be careful here. The domain is not all real numbers. That is not the domain here. That would be the domain if you had f of x equal to like 3x. The domain here is the set of all points in the xy plane. So there's not a good way to write that. Well, there is a good way to write that, but it's not a way we typically talk about. So the domain is all points in the xy plane. Let me show you two other ways to write this just because you should know them. This one I don't think you'll come across, but you could write it as the set of all points x comma y such that x and y are both real. You could also write it as, instead of just the fancy R for the real number line, you could write it as, now I'm going to say this the way it's said, you could write this as R2. We do not say R squared. We say R2. Why? Good God if I know, but that's what we say. Nobody says R squared. You say R2. So yeah, so that is another way of writing the entire coordinate XY plane. Yeah.
This R and the other R.
Oh, well, so this R is just the x-axis. Everything from negative infinity to infinity. The real number line. Whereas this R2 is the XY coordinate plane. So it's everything in the XY axis, the two-dimensional coordinate system. So when I talk about the domain being R2, it's all the points that are in the two-dimensional plane. The point 1, 5, the point 3, 7, the point negative 2, negative a million, right? Any point where x is a real number and y is a real number is a point that is in the domain of this function of two variables. Yeah, I like it. Okay. We'll stick with domain. We're going to come back around and maybe graph this and talk about some level curve stuff. But let's talk about domain for another minute or two here. let's look at, yeah. Oh, actually, before we talk about domain, so here now to kind of change things up a little bit. If we talk about the range of this function, so the domain consists of an X and a Y input. You have to have an ordered pair. You can't just say like there's one thing. It has to be the point 5, 3 or 2, 7, right? For the range, though, the outputs are just real numbers. If you input, 3 and -2, you get out 0. If you input 1 and 1, you get out -2. For every input that's a coordinate pair, you get an output that's a single value. So your range is going to be just real numbers. In this case, the range is going to be all real numbers because you could certainly find an X and a Y value that would give you any real number you wanted as an output. I don't think I need to do. Well, I could, for example, no, sure. You could say if I'm trying to solve this, set this equal to C. I don't know why we choose C, but we do for some reason. It's kind of the letter of choice when you're trying to show that something's in the range. You could say, oh, well, I'm just gonna let Y equal 2 to make that 12 go away. And then if I do that, then I've got 12 minus 8x minus 12 equal to C. This seems kind of contrived, I know, but bear with me for a second. The 12s cancel. Solve for x, and you get x equal to -C/8. Here's the point. For any C value, for any real number of C, we can always find an XY pair that will give us that C value as an output. In this case, and I've kind of made a choice here. The pair I've made is X is going to be -C/8 and Y is going to be 2. That pair will always give me whatever C value I want. So if C is 1 billion, then my XY pair is -1 billion/8, 2. If C is 5, my XY pair is -5/8, 2. And that'll always give me the desired C value. That shows me that I can get any real number as an output, which means my range is all real numbers. Like that. My hands are really cold. If you have questions, you're always welcome to ask them. And we can always come back to things if you're like, oh, I had a question. Let's move on to, we'll do a couple more examples and then let's do that. Okay. Let's look at this next example. And we're just going to talk about domain and range for a few more minutes. So let's say our function, let's do this one. F of x, y. Oh, this is example. I try to number things for like a minute and then I forget. We'll try this though. Say number 2 is f of x, y equal to sine of 3x minus y. Oops. I don't see any of the three things. No fractions, no logarithms, no square roots. Domain, probably not any issues. I should point out, if you had like a tangent function or a cotangent or a secant or a cosecant, even though you don't see it, there is a fraction there. Right? Tangent is sine over cosine. Oh, the bottom could be 0. So if you see tangent or cotangent or secant or cosecant, there is a fraction you have to pay attention to. Here, no fractions, no square roots, no logarithms. So the domain is, I really wish there was a better way of writing this. I'm just going to say R2. Everything in the XY plane. Or I really should say all points in the XY plane. What about the range? What's the highest value the sine function can have? 1. Can we get to 1? Can we pick an x and a y so that we would end up getting sine equal to 1? Oh, what do you have to take sine of to get 1? Cosine of 0 is equal to 1. Sine of 0 is equal to 0. The next angle, it's the, thank you, yes. So sine of pi over 2 equals 1. And I could definitely pick an x and a y that would get me pi over 2 as the input. I could pick the point where x is 0 and y is -pi over 2. That would totally work. that would give me sine of pi over 2 equal to 1. And similarly, I could pick x equal to 0 and y equal to positive pi over 2. That would give me sine of negative pi over 2. And if you go clockwise down to the bottom of the unit circle, that's where sine is going to equal -1. Cool, we get the whole, well, I wouldn't say we get the whole range. We get the largest range you can ever get for a sine function, which is as low as -1 to as high as +1. So here our range is exactly that. Bracket -1 to +1. Okay. Yeah, we'll do one more. Yeah, one more of those, and then we'll do the funky one. Yeah, let's do that. Cool. 2 more for domain and range, and then we'll talk about some graphing stuff. Let's say we have the function g of x comma y equal to the square root of x plus the square root of 16 minus x squared minus y squared. We definitely cannot combine these square roots together. If we could, we probably would have written it that way in the first place. Excuse me. So I see some things that require attention, right? We have square roots, and we know when we have square roots, we have to have the argument being non-negative. So I have 2 inequalities I have to deal with here, and I should really just deal with them separately. Here, I get to say that x has to be greater than or equal to 0. And really, with the exception where the domain is everything in the xy plane, usually it really makes sense to draw the domain, which we're going to do in a second here, but I want to kind of deal with both parts first. Here, again, we need the argument of the square root to be greater than or equal to 0. Does anyone remember what I said about x squared and y squared last time? I know it wasn't like super clear exactly what I said, but kind of what I said was they should stay together. If you've got an x squared plus y squared or a negative x squared minus y squared, you should keep them together and kind of move everything else away from them. I like them both to be positive personally, so I would add them both to the other side. I would rewrite this as 16 is greater than or equal to x squared plus y squared. If you prefer, you can move the -16 over and then multiply both sides by -1 and change the inequality. It's the same thing. It's just a different way of getting there. So x squared plus y squared equal to 16. That's a circle, radius 4, centered at the origin. So if I start graphing things, so I want my circle, radius of 4. Now, I don't want to draw too much here before. I don't want to get carried away. So I know I need x to be greater than or equal to 0. So that means I need to be on which half of the xy plane? Top, bottom, the left, the right? If x is bigger than 0, that means I need to be over to the right. X could be 1 or 2 or 3, which is over to the right. If y was greater than or equal to 0, then I had to go up. But since x is greater, so I'm really, this half is out. I don't want to shade in this entire half though, because I also have to deal with this restriction here. The x squared plus y squared is less than or equal to 16. So I'm going to draw the circle. X squared plus y squared is equal to 16, except I'm not going to draw the left half of it because I know that side's already out. So I don't need to bother with it. And I'm going to draw it as a solid circle, not dashed, because I know it's a greater than or less than or equal to. So I want to include the boundary. I'm going to draw this as best I kind of made my x scale a little too large here. Oh, well, sometimes that happens. Ooh, that's a circle. We're pretending it's a circle. So there's the right side of my circle. Yeah, it doesn't look very circular, but we can all pretend it's a circle. And then, okay, now the question is, do I want everything inside of the circle or outside of the circle? Well, pick a point. Pick a point that's not on the border. So I'm going to pick like 1, 0 and test it to see if it works. So I put 1 for x and 0 for y. Is 16 bigger than or equal to 1 squared plus 0 squared? Yeah, it is. So I want everything that's inside this boundary here. So I want all of this. And also this. But that's it. Just the stuff inside this half circle and the boundary. Nothing outside of it, nothing to the left, because x had to be greater than or equal to 0. There really isn't a good way to write this domain. The best I could come up with is, and again, it's not very nice, it's the set containing all points x comma y such that x is greater than or equal to 0 and x squared plus y squared is less than or equal to 16. There's not a nicer way to do it. That's it. That is the best. Normally, people are not asking you to write the domain like this. They're just asking you to draw it. Drawing it is much more informative. Oh, nice. I know yeah, I know. I know. Some habits just won't die. Questions about this before we do one more? Okay. One more. It's going to be a little bit funky. It's going to be kind of similar, actually, but different. We're maybe, yeah, well, we'll see about drawing this thing. So let's say now we have a function f of x comma y comma z. So now it's a function of 3 variables. And it's going to equal, yeah, it's going to be super gnarly. Give yourself some room here. X squared times y to the 5th times the square root of 3 minus x minus y minus z plus the square root of x plus the square root of y plus the natural log of z. Seems unnecessarily complicated, but not really, actually. So first I want to point out, since this is a function of 3 variables, which we're not going to encounter very often, but occasionally people like to talk about them, our domain is going to be not a region in 2-dimensional space, but a region in 3-dimensional space. It's going to be some volume of domain. All right. We have a few easy restrictions. This part, and this part tells us x has to be greater than or equal to 0. That tells us y has to be greater than or equal to 0. And this tells us that z has to be strictly greater than 0. Or as I would say, and in fact, I will say, it means we're stuck in the first octant. So just like in 2-dimensional space, we use 2 coordinate axes to cut it up into 4 equal quadrants. In 3-dimensional space, we use 3 axes. Typically with the x-axis pointing out towards you, the y-axis pointing to the right, and the z-axis pointing upwards. And just like in 2 dimensions, the first quadrant is where both x and y are positive. In 3 dimensions, the first octant is where x and y and z are all positive. So it's this front upper right corner. Typically, unfortunately, there's this thing here. Often when I think about the room, I think about that corner down there, which I know is not easy for you on Zoom to see, apologies. But imagine if you're sitting in a room and you're looking forward, it's the corner that's to the front, left, bottom part of the room. That corner right there is the origin. And that edge right there is the z-axis pointing upwards. That edge right there, which is not perfectly straight, oh well, is the x-axis pointing out towards you. And this edge down here is the y-axis pointing to the right. And then you'd also have the negative y-axis pointing to the left, the negative z-axis pointing down, and the negative x-axis pointing to the room behind us. Cool. So I have one more thing to deal with as far as domain here. I've also got that 3 minus x minus y minus z had better be greater than or equal to 0. So typically when you see something like this, you want to get, at least I want to get the x, y, z on their own side. So I would rewrite this as 3 bigger than or equal to x plus y plus z. Or probably x plus y plus z less than or equal to 3, just because it's more normal to write the variables on the left-hand side. Okay. What kind of thing is that? Well, that's not a good question, James. Let me ask you a better question. And this is typical. Whenever I'm trying to think about an inequality, I'm really thinking about the equality. I'm not really seeing that as x plus y plus z less than or equal to 3. I'm thinking it's x plus y plus z equal to 3. And then I'm going to figure out which side of that thing I want. So x plus y plus z equal to 3. Well, there's kind of a two-dimensional analog. If I was going to graph x plus y equal to 6, even though it's not written in the usual way, what kind of graph does that equation have? It'd be easier to think of maybe if I solve for y. But what shape is that? I know you know. And you just don't want to say it. It's a line. It's totally a line, right? If you solve for y equals 6 minus x, that's totally a line. One way you can see that this is a line is that every variable is raised to the first power. It's a linear function. That's also true over here. This is linear as well, but the problem is we have more freedom. So here, instead of getting a line, we're going to get a plane. The easiest way to graph a line, graphing the intercepts. I would get y equal to 6, x equal to 6, I'd graph that line. The easiest way to graph a plane is getting the intercepts. So if I set x and y equal to 0, I'm going to get z equal to 3. If I set x and z equal to 0, I'm going to get y equal to 3. And if I set y and z equal to 0, I'm going to get x equal to 3. Now, I will point out my drawing skills are not amazing. There is an entire infinite plane that we're about to not draw. We're just going to draw the triangle that it intersects. Right, but you can imagine this triangle being, right, it's kind of like, yeah, it's a great idea, James. Let's do that. 1 second. I will point out, you do get more coming to class in person because you're able to see all the things I'm doing. So not that you shouldn't come on Zoom if you want to, but there's a higher quality experience if you come in person. So imagine this is the triangle I just drew, and this is the plane it's sitting in. That goes on and on and on, right? I just haven't drawn all that because it's hard to draw, to be honest. Now, that's bounding our domain, right? We said, oh, we don't want x plus y plus z equal to 3. We want x plus y plus z to be less than or equal to 3. So say this point here, the point 1, not 1, 1, 0, because technically z can't be 0. Let's pick 1, 0, 1. So I've gone 1 in the x direction, 0 in the y direction, and 1 in the z direction. There's the point 1, 0, 1. And if you look, that point definitely satisfies the inequality. So the points on the side of the plane that are closer to the origin are the points that we want. So it's kind of hard to draw it in here because it's literally the entire solid. But basically, I want everything inside this tetrahedron except for where z is equal to 0. So I don't want the bottom plane there, but I want like everything above it. And again, drawing this is not a smart idea. Really, I should probably not have colored this in like this. But basically, you've got everything inside this tetrahedron. That triangle, the bottom face, the left face, the back face. That would be your domain. All the points inside that solid. Normally, most of the time, we don't go that far. Usually in this class, we're looking at functions of 2 variables, but there were 1 or 2 questions on the homework assignment that had you looking at functions of 3 variables. So I thought we should do an example. Okay. Questions so far? Well, I did kind of ignore that, yeah, because although they are certainly part of the function, they don't play a role in determining the domain. When I'm looking at domain, what 3 things am I looking for? What's one of the things I'm looking for? Square roots. What's another thing I'm looking for? Fraction. What's another thing I'm looking for? Right. Those are the 3 things you should look for. If you don't see any of those, again, with rare exception, also inverse trig functions have restricted domains, but I don't think we're going to run into those. So those are the only types of functions that have restricted domains. Fractions, even roots, right? Not just square roots, 4th roots, 6th roots, etc., and logarithms. Okay, let's talk a little bit more about the graphing side of things. And yeah, let's see. Notes. Yeah, can I keep things in order here? Maybe. There we go. Yes. Oh, I lost a page. The only page I need. Sorry, one sec. You're not it. Are you it? No. Sorry, sometimes I'm not 1000%. No, that's not the right one. I had you in my sights. Whatever, let me hand things out while I'm trying to find the one piece of paper I'm looking for that I had a minute ago. So, yeah, everyone. We'll hand this out somewhat willy-nilly here. I have to do one more case. There's extra, just put them on desk next to you. And then also these as well. Okay. They would probably fall on the ground somewhere like looking. Problem with having too many pieces of paper is then you start to lose your mind. Okay, one more chance. There we go. I found it. Magically hiding from me. Okay, so what's that? I can definitely excuse me. Yes, I can put those on. I can add those to Canvas for sure. And I will. Oh, nice. Just spit on the notes. That's lovely, Jane. Wow. Good job. Okay. So let's look at this for a second. This is not something I hand out to you just yet, but I want to look at this again first because it's pretty. It's nice and colorful. You can see it. So this is a contour map, contour chart. You can think of it as oh, there's another word for it. What do you call those maps? Topographical map. Thank you. Yes. The idea basically is this map is showing you lines of elevation. This one's I think supposed to actually represent heat. So I just want to point out, if I ask you, how hot is it at the coordinate 6,7? Well, I'd go over to 6 for the x coordinate, 7 for the y coordinate, find where they meet up, which is right about there. And then notice that I'm in the yellow color. So the heat, I'm going to say is 15 because it's between 14 and 16. So at 6,7, or I should say the temperature at 6,7 is 15 what degrees? I'm making things up really. Or I could ask you, what's the temperature at say 2,3? Well, we have to go over to x is 2, y is 3, locate the point on the thing, and then find what elevation or what temperature we are at. The colors here are not lovely. I think it's that color, so I'm going to say it's 11. But that's kind of the idea. You're basically looking at the map to see at this coordinate what height you're at, what value you have. And it could be, right, you could be measuring temperature, elevation, barometric pressure, lots of wind, like many different things can be put on the topograph. Often elevation is the most common example. And so just as a kind of extension to this, if I were to say, start here and move, I don't know, really any direction, but say I wanted to move to the west, assuming that we've got a northeast, southwest kind of situation here, is the temperature getting warmer or colder? Colder, right? The temperature is decreasing if I move to the west from that point. On the other hand, if I were to start, let's say, pick a more interesting point here, James. If I were to start right here and move to the west, am I getting warmer or colder? What do you guys think? Warmer? Colder? No, warmer, right? Because we're going from a lower value to a higher value, from a lower temperature color to a higher temperature color. On the other hand, if I went the other direction, if I were to go to the east, which I hope I said west last time, right? Okay. Sometimes I'm not good with east and west. It's terrible, I know. If I went to the east, I'd be getting colder. So direction of travel, your function's typically either going to be increasing or decreasing depending on which way you're going. And one more thing I'll say, because this actually does come up quite often, we're going to talk about it probably next week, is if I start, say, let's say here, and I want to travel in the direction that's going to get me the warmest, the fastest, I would want to travel in a direction that is perpendicular to the lines of, to the level curves is what we call them, to the top, to the lines that mark off when things change. So if I wanted to get warm fast, I would go that way. Because that's the way I'm going to cross into a higher temperature area the fastest. And it is definitely a direction that is perpendicular to the lines that mark off the temperature changes, also known as the level curves. And that's an idea that's going to definitely be recurrent throughout the next few weeks. What I'm talking about here without saying the word is something called the gradient, which we're definitely going to be talking about. Okay, let's grab let's see which handout. Let's look at that. Did I give away all those other ones? Sorry, let me grab one of those. I need one of the, yeah, I appreciate it. Sorry, this one. Or all of them. Let's go with that. So just to kind of drive the point home, right? Here is a picture that's kind of showing what you see versus what you'll actually be getting, right? You might see a topographical map like this, and the point is that we want to be able, excuse me, we want to not burp so much. It's a problem with having class right after lunch. So yeah, I know. So we want to be able to look at this and understand that this means we have a peak here, right? You can see elevation 0, getting higher, higher, all the way to the peak here. The closer the lines are to each other, the steeper the ascent. The further the level curves are apart from each other, the more gradual the ascent, right? Because typically they're at kind of the same difference in heights, right? 0 feet, 500 feet, 1,000 feet, 1,500 feet, right? Every difference is 500. So if those are closer to each other, then you're ascending that 500 feet in a shorter distance, as they're farther apart in a longer distance. That's kind of all I really had to say about this picture, but I think it's a nice picture to look at, right? Because we're definitely going to see things that look like that and kind of have to figure out what the actual surface of the mountain or the surface is the right word, what the surface looks like. There's not a better word, it's a surface. Time is okay. Time always goes by so fast in this class. And then this handout was just kind of to allow you to have a chance, like I might ask you, okay, here's the topographical map, aka the contour map, or the graph of level. These are all the same thing. Graph of level curves, contour map. I think the contour map is, I think, the phrase the book likes to use, or topographical map is a fine way to think of it. Here's a topographical map or a contour map of some function of two variables, right? So what we want to do is I want to know maybe like, what is f of 1, 2? Sure, yeah. What's f of 1, 2? Approximately. Well, if I go over to x equal to 1 and y equal to 2, it's about right there. Let me ask you. We'll set boundaries instead of saying what it's actually equal to. I don't know what it's actually equal to. But what two numbers am I between if I'm right there? Good question. Which numbers am I between? Well, I'm between these two level curves, and these two level curves have values of 0 and -1. So I don't know exactly what f of 1, 2 is. It might be like -0.5, but I know for sure that it's between -1 and 0. That is not the biggest you could be writing, James. Be writing much larger. Sorry, it's hard to see. Or if I said, I don't know, what's f of, sure, 2, 0. Well, then I would look over to, I have to be careful here, right? Because the numbers are not super well delineated. There's x equal to 1, there's x equal to 2. So there's f of 2, 0. It's actually on one of the level curves or one of the contours. It's on the contour where the function value is equal to -1. So f of 2, 0 would equal -1. So if you were to try and actually graph it, like, so what you could do, if you were better at drawing than me, which many of you probably are, is the idea is you kind of want to stack these up, right? This outer one is at a height of -2. The next one's a height of -1. The next one's at a height of 0. The next one's at a height of +1, and then a height. I can maybe draw this. I'm gonna try and draw it. We'll take our chances here. Okay, so okay. He said confidently before he started trying to do it. So, yeah, I'm less sure of myself now. But let's see here. We've got, so down at -2, we've kind of got, yeah, okay, it could be better. I'm not gonna lie. But then as we go up, it goes in a little bit. Ooh, wow. Okay. Yeah. All right. So yeah, my drawing. Okay, let's pretend like, you know what we could do though? Why try to draw something when you've got really good tools at your disposal? Except I don't know what this function is, so I could probably guess though. Anyway, I don't know what it is. I didn't think that far in advance, unfortunately. Let's use our time wisely instead of me just screwing around up here. So let's talk about actually graphing some contours, because that is something you do are required to do sometimes. And it kind of goes both ways. Sometimes you are given the function asked to graph the contours. Sometimes you're given the contours and asked to identify what the surface might look like. And actually, let's go back to something that's not too terrible, like f of x comma y equal to 12 minus 8x minus 6y. And I'm going to point out that this surface would be a plane, because you could also write it as z equal to 12 minus 8x minus 6y. In fact, just like in 17a, how we would often replace f of x with y, because they're kind of the same thing, here we often think of replacing f of xy with z, because they're kind of the same thing. Not 100% all the time, but enough of the time that it's worth to kind of make that connection. So the idea here with graphing level curves or contours is you're picking the height of your function. Saying, I want to know what's going on at the height of 0, or a height of 1, or a height of 2. Now, this gets tedious. Let me show you a couple of them. Let's say we set z equal to 0. Well, then I'm going to have 12 minus 8x minus 6y equal to 0. I don't know what that looks like exactly, but I know what's a line. And I could solve for y. Negative 6y equals 8x minus 12. Y equals negative 8/6x plus 2. So great. I know that when z equals 0, I have a straight line. Slope is negative 8/6, which is negative 4/3. The y-intercept is 2. So it looks something like this. Sure. I guess I could find the x-intercept. It's terrible. Yeah. Fine, I actually have to do the math. So if x is 0, y is 2. If y is 0, x is going to be 8/6, x equal to 2. X is going to be 12 over 8, which reduces to 3 over 2. Okay, so there's my level curve when z is equal to 0. And then I could do it again when z is equal to 1, for example. So z is equal to 1. You can see how this is going to be really repetitive, I think, right? If I do it again, I've got 12 minus 8x minus 6y equal to 1. I subtract 12, I add 8x, so I get negative 6y equal to 8x minus 11. Then I get y equal to negative 8/6x plus 11 over 6. Same slope, slightly smaller intercept. I should say slightly smaller y-intercept, right? The y-intercept is 11 over 6 instead of 12 over 6, which was 2. So I move down just a little bit. And there's my next level curve.
Let's say Z is 1.
It does, yeah. Yes. Okay, here's what usually ends up happening when people do this. They say, screw this, I don't want to do this many times. So what we do instead is we say, I'm just going to pick a value c for what I'm setting z equal to. And I'm going to solve for y in terms of c. So let's give ourselves a little bit more room to work with here. Let's say set z equal to c. So then I have 12 minus 8x minus 6y equal to c. And I'm going to solve for y, just like I did before. So negative 6y equals 8x minus 12 plus c, or maybe plus c minus 12. And then dividing by negative 6, I get y equal to negative 86x. Yes, I know that reduces. I just didn't reduce it. Negative 12 divided by negative 6 is plus 2. And c divided by negative 6 is minus c over 6. So for whatever value of c we pick, we're going to get a straight line whose slope is negative 4/3 and whose y-intercept is 2 minus whatever c over 6 is. So when c was 0, our y-intercept was 2 minus 0. When c is 1, the y-intercept is 2 minus 1/6, which is 11/6. And as the larger the value of c gets, the lower the value of the y-intercept is going to get. So we can see that if, for example, c is equal to 2, the y-intercept is going to be 2 minus 2/6, which is 10/6 or 5/3. And so we could draw another line here. And again, these are kind of close to each other. So what we can see, and that's when z equals 2. So as your height increases, your straight line moves down. Okay. How much time have I got? Okay. So here's kind of the translation of these level curves to the actual surface. We know it's going to be a plane already, but let's take a look. If I was going to try and graph this plane, z equal to 12 minus 8x minus 6y, I want you to see a couple things here. My usual coordinate axis system. And we know when z equals 0, we're going to get the line. I know you can't see it because I'm pointing to it up here. When z was 0, we got the line y equals negative 86 x plus 2. I don't actually want to graph that though. What I really want to do whenever I'm graphing a plane is just graph the intercepts. So here my intercepts are kind of large. My z-intercept is 12, 2, 4, 6, 8, 10. Let's say that's 12 there. My y-intercept is positive 2 or negative 2. I hope it's positive 2. Otherwise I'm in trouble. If that's 0, that's 0. Yeah, that needs to be 2. If z is 0, I know I didn't quite say this explicitly, but when you're finding intercepts, you're just setting the other variables equal to 0, right? Just like in 2 dimensions, when you find the y-intercept, you set x equal to 0. In 3 dimensions, to find the y-intercept, you set x equal to 0 and z equal to 0. So here, if I set that equal to 0 and that equals 0, oh yeah, I need y equal to 2, which is right there. And then if I set z equal to 0 and y equal to 0, I end up getting 0 equal to 12 minus 8x. 8x equals 12, x equals 12 over 8, which is 3 over 2. It's about right there. So here's my kind of really steep looking plane, which again extends in other directions. And look, here's one of my level curves. There's the level curve where z equals 0. And just slightly in towards the origin, here's the level curve when, say, z equals 2. And the higher we go, the further back towards the origin we go. We could also go lower though, right? We could go z equals, say, like negative 2, and we'd be coming down and forward and getting something kind of like that as our level curve, where z equals negative 2. So the level curves are just what the graph would look like in 2 dimensions at a particular height. How much time? Yeah, okay. Let me see if I can, try and give you one more example that's a little bit nicer to look at. Yeah, paper everywhere. Yeah, of course. So one more example. This is kind of an example that we come back to often because it's nice. Let's look at the function f of xy equal to 9 minus x squared minus y squared. And we'll talk about level curves for a second. So I'll point out no domain restrictions. X can be anything, Y can be anything, X and Y can both be anything. Domain, everything. The range on the, the range on the other hand is limited. The biggest this function can ever be is 9. And that's going to occur when X is 0 and Y is 0. If X and Y are anything but 0, we're going to be subtracting off and making it smaller. So our range here is everything from negative infinity up to 9. Let's look at one level curve. Let's say we're going to set z equal to, let's say 8. If z equals 8, I have 9 minus x squared minus y squared equal to 8. Or x squared plus y squared equal to 1. Oh, I get a circle. So at z equal to 8, I've got a circle of radius 1. I'm cherry picking some values here because, well, time's almost out. Let me pick one more. Let's say I pick z equal to 5. Lower, right? I started at 8, got a little circle. I'm going to go lower, and I'm going to get, well, let's see. 5 equal to 9 minus x squared minus y squared, or x squared plus y squared equal to 9 minus 5, which is 4. The circle of radius 2. So here at z equal to 8, I've got a small circle. Here at z equal to 5, I've got a larger circle. So up top, we've got a small circle, larger circle. What do you think is going to happen if I go down further? Larger or smaller circle? Larger circle. So as we keep going down, we get larger and larger and larger circles. But every level curve is a circle. Every horizontal slice through the surface is a circle. It's kind of like your surface is an orange. And when you cut the orange horizontally, the level curve is the surface you see, which would be a circle for an orange. So here's what this thing kind of looks like. It's called a paraboloid. It looks like a parabola. It is a parabola. It's been rotated around the z-axis. I kind of think of it as a mountain, right? The peak is here at the point 0, 0, 9. You've got some intercepts here at 0, 3, 0, and at 3, 0, 0. And if you draw some level curves, here's the level curve when z equals 8. Here's the level curve when z equals 5. And down here is the level curve when z equals 0. It's a circle of radius 3. So that's a brief overview of kind of what level curves are, how they work, and how they fit in with the surfaces. And yes, you're all welcome to go. It's 2:01.